All right, this is part 2 of magnetism. And why we have magnetism is because the flow of current. Okay, so we're going to do a couple new right-hand rules today. So last time we learned about one right-hand rule, which is to find the force, direction of force of a charged particle moving with such a velocity in the magnetic field. Remember, this angle is the angle between the V and the B. It's actually a cross product, V times X. Okay, and we had a right-hand rule to find the force. The velocity is denoted by the thumb. The magnetic field is denoted by the fingers, which way they point, and the open palm, that means there's an inward force into the screen in this case for that particular one. That's the right-hand rule, the first one we learned. We have 2 more to do today. So magnetic forces are on, so anytime you have a current, it's going to have a magnetic field. So if you have an external magnetic field, it'll push on that thing. Or if you have 2 currents, you're going to make 2 magnetic fields. They can push or pull on each other, depending on whether they're long straight wires, solenoids, or otherwise. Alrighty, so first force in a B field current. So here we have a velocity of something, and the velocity is in this direction, okay? But the field is in that direction. So which way is the force on that charged particle? Do you remember? Do you remember? Do you remember? It's out of the page. That's that right-hand rule we just talked about. The velocity is in this way. The field is where my hands point. That means this is pointing out of my palm. It's coming out of the screen or out of the page for the right hand. That's the first one we learned. Now, what if instead of a charged particle, it's actually the flow of current? So now you have the flow of current going in that direction. The field's in the same direction. What's the force on that wire? It's actually in the same direction. It doesn't matter if it's a charged particle or a whole wire, the force is going to be the exact same direction on that thing. And remember, current is charge per time. So if you want to find charge, it's just current times the time. And velocity is this distance or the length it travels per time. We're going to do a little quick math here to give you a new formula. So that's a force on the moving charges, but we have a whole line length of charges that you're pushing on. So what we're going to do for the Q, we're going to do a little substitution here. And what's going to happen is, so the V times T is going to become the L, and then the Q over the T is going to become the I. So you notice what we did is we took it times time and we divided it by time. Just did a 1 over 1. So we took it divided by time, that's going to make that an I. Took the velocity times time, that's going to make that a length, or the length of the wire in the magnetic field. Sure, the wire could be longer. The only thing that counts is the actual length of wire right here that's in the external magnetic field. Bam! There's your new formula. So it's really the same thing as this up here. We're just using on a practical cases. We don't have a charged particle moving. We have a whole wire in that magnetic field. So that's the flow of current. We don't measure charges when you're talking about what's flowing in a wire. We're talking about the current flow, which is easily measurable. And you can do the length pretty easily, and as long as you know the magnetic field. And remember, that is the, as far as what is crossed what, well, the length has to do with the velocity. It's really the length to the B. Okay, so it's what direction all that stuff is compared to the B. So if the V goes in the same direction as the B, this velocity or the current goes in the same direction as the B, there's not going to be any current. Whoops, that'd be an I cross B then, wouldn't it? Not necessarily the length, but however you want to think about that. Okay, but at the same point, it's out of the page. The charge is moving in the exact same direction. Now let's say if we have a whole coil of wire and the current goes in a circle. For whatever reason, it's going in a circle. Alrighty. So what is the direction of the force on this A to B? Well, it's moving in the same direction as the magnetic field, so what's the force on that wire? Nothing. Okay? So on the AB, there's actually 0 force because they're in the same direction. So there is no forward force. And the reason is we're about to learn a little bit of that, something I showed in the demonstration, the current flowing around that red spot from A to B. It's wrapping perpendicular. The magnetic field on the wire is actually wrapping perpendicular around it, and perpendicular magnetic fields can't push on each other. More on that in a moment. Let's look at the, okay, so there's your angly stuff with the I versus the B right over here. So there is no angle between the I and the B. That means there is no net force. So the B is kind of in the middle, but it's really between the I and the B, though. There's a cross product there. Okay? So there's no angle, there's zero force. Hey, how about that C to D? Well, you can do your right-hand rule stuff. You got a magnetic field going like this. So magnetic field goes like this. The current's going upward. That means that's an end of the page. Hey, we got a force on that wire that is, in fact, wait for it, into the page. Because what happens is, if you think about it, the rule we're going to learn in a little bit with the current going across that wire is going to be a right-hand rule going this way. On that side, there's going to be a magnetic field from the wire going into the page, and that's kind of what they're showing you there. That is, as it wraps around there, that's actually, they're going to show you the net force vector is what they're showing you, not the magnetic field, even though it does wrap around in that direction, that there's a net force that way on the wire. How about C to D? What's the force there? Once again, it's anti-parallel, so that means that force is zero once again. Hey, C to D. That's coming out. Okay, so you got this going downward like this. Current's going downward like this. And the field is that way. Which way is the force then? Well, that's going to be an out of the pager, isn't it? From D to A. Oh, that was the last question. Now we're doing the D to A. I got ahead of myself. Okay. Well, if you do the force, what direction of the force on the D to A wire? Well, that's going to be out of the page. Okay, here we go. There you go. Now they're showing the force with the missile coming right at your face. That means there's a net force in that direction. Okay? Alrighty. So finally, the torque on this loop in the magnetic field. So remember, we have a force inward there, no force, and a force out. Well, now you have a twist. Is there a net force on the loop? No, there's no net force on it because the whole loop's not going to accelerate anywhere. It'll spin. So that's the little tiny lesson we had in AP1 about torque. Torque is a force times some kind of lever. It's going to spin about the center of mass of this thing. So there's your force, there's your lever downward, here's your force, here's your lever this direction, and that's upward. You got to twist around this. So there is in fact a net torque or twist on this thing, but there actually is no net force because that force into the page is the same as the force out of the page. So the loop doesn't really change positions, but it does spin because you have no net force, but you do have a net torque on the thing. Torque is not zero. Okay? So what happens is you have a force downward here, a force upward. That's going to twist. And it's going to twist in this direction, clockwise. Now, you might be thinking, hey, what happens as it gets higher, though? What happens? Okay, so that will spin. So there we start out there. It's going to spin in place. But what happens when it spins to there and then goes to there? Well, the force is upward. Well, what's happening to the angle between this and the length of this thing? Eventually, that force will be straight up, and this force will be straight down. So we still have a torque. So we still have a torque here, but look what happened to the lever arm. It's shorter now. We have a shorter lever distance, because remember, for torque, it's the perpendicular force to the lever. And the lever, even though it's like this, you have to use a little math to find out what this perpendicular distance is to the force. And that's a smaller lever. That means there's less torque. Maximum torque was right over here, perpendicular, but this is less than that. And then what happens as the thing goes straight up and down? So the forces are small. I mean, they still have the same forces, but the torque is actually less because this lever distance is smaller. So actually, if you want to find out what the torque is, it relates to this angle. When this angle is 90 degrees with the wire right here, when this is 90 degrees, well, that's maximum torque. But as you get closer to 180 degrees, you're getting closer to minimum torque, which is what happens when you get straight up and down. Because you get straight up and down, which hopefully we'll show you in a minute. Remember, that is, okay, by the way, we're doing an area loop here in a second. Looks like we did in Gauss's law. Because that length of the wire times the width, that's basically your area of the whole thing. So we're talking about an area vector in a moment with the area of that loop. Okay? So if we want to find the torque, rather than talking about the length and the W, really all that matters is what the area is. It doesn't matter the shape of that. It just means the area of the loop. So this is a formula to find what twist you have on a coil of wire, which is an electric motor. It's exactly how electric motors work. You get your maximum twist when it's this direction, but as it gets closer to perpendicular, you approach zero torque. Okay? Because as soon as that sign is 0 or sign 180, well, that means that's at 0. There's zero torque whatsoever. So let's go straight up and down here. Oh, we'll get there in a moment. So what is the torque on the loop below? Okay, so first of all, you've got, if you're doing a right-hand rule, on the top, you've got current going this way and the magnetic field in. So there's a force upward on the loop. Okay, let's go down to this side over this side. That's what I did the top. Let's go to this side right over here. It's going downward. Now the force is outward. Okay, now we're down here. We're going right-hand rule. The magnetic field's in, the force is down. And then we get to this side over here. The force is out. So the force is out, 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 out. What's the net torque on the whole thing? There's the force there. There's the force there. There's the force there. There's the force there. So what's the net torque? 0. So the best answer is less than that amount because there is no torque whatsoever in that configuration. Okay? So in that configuration, the forces are in the direction that there is no net torque on that thing. So if your motor is lined up like this in that external magnetic field, it actually doesn't spin. You have to sometimes, in these cheap little motors that only have a few coils all in the same direction in one magnetic field, you got to sometimes twist the motor to get it started in case it's stopped in this orientation, because when you try to start it up again, there actually is no net twist on it. Okay, so here we go. So we talked about this. So this is the normal, okay? So this is the area vector of the whole thing. That's the angle that we're talking about over there, okay? So to find the maximum torque, you want it at 90 degrees, of course. That means as you're straight up and down, there is no torque. So what happens is you get maximum torque here, minimum torque, but something in motion stays in motion. Now the problem is, depends on how you do your motor. If you didn't do anything on your motor, that means you're going to have a backwards torque as soon as you hit here. And that's not a very good motor. But there's cheap and easy ways to fix this, so you'll have a push on one side, then you have it so when the wires make connections, they make no connection, and motion stays in motion until it comes back around, that does another push, then a push, then a push. That's how your cheap little motors work. And we would, if we were in class, we could make those cheap little motors pretty easily in an external magnetic field, but they only get a push on one side if you set it up right. If you always have it set up so there's a current running through there, you can actually get a backwards push, which doesn't help you on the motor. Okay, so as we talked about in the demo that I also have, is that if you have more loops, you have more wires that have a magnetic field, you're making the magnetic field of the loop even greater, you're going to get a greater torque. So this is just for one little loop, so if you have ideally 10 of those loops with the same current, technically that would be 10 times the magnetic field on that loop in that external magnetic field, meaning you have 10 times the force on it, meaning 10 times the torque. So this is an idealized thing, that if you have more loops, 10 loops, you'd have 10 times the amount of torque or twist on that thing. Okay, there are actually other factors that go into this, because the more loops you have, the more resistance you have, tends to make your current smaller. Not only that, but there's a term called impedance that you can run into, which is when you have a variable resistance depending on how quickly the current is going through, in case it's an AC motor or the current's actually changing, going on and off, on and off. So it gets a little more complicated, but basically, more current, greater torque. Number of loops, more current, greater the area. Because you have a longer lever, the greater the area, you get more torque. And of course, more torque at 90. Alrighty, we're down to our final 40-some seconds. So it doesn't matter if it's rectangular or not, or round, or whatever the shape. That's the beauty of it. All you have to know is the total area. So it may be a funky shape, but that doesn't matter if it's a funky shape. You're still going to get the same net torque out of the thing. A push one way and a push the other way, you get the same torque. Okay? So as you get up to here, the force is, there is no force whatsoever. So you're relying on your electric motor in motion to stay in motion at that point. Or you have another set of coils or another external magnetic force that can start pushing on it in that case. So there's different things you can do on the powerful motors. They have what's called a three-phase motor, which they're set up all at 920 degrees from each other. And so you get more of a constant push, not just here.